Hi, so we'll be learning about some important terms in paging, in operating system paging. So as you can see here, the first term is logical address. Okay, so here, what is logical address? So this is a process. So let me show you. So this is a process. Okay, and this process has instructions stored in it. Okay, obviously a process is a set of instructions. Now an instruction size can be of any bytes. Okay, but there is an address given to each memory location of a process. Okay, so for example, this particular location is 1 byte. Okay, and this is also 1 byte. Okay, so these are the 1 bytes smallest unit of addressable smallest addressable unit of a process. Okay, and this is what we call logical address. Okay, this address is known by the CPU only. So whenever CPU executes a process instruction, for example, let's assume for simplicity that an instruction is of 1 byte only. Then this 1 byte, the first 1 byte instruction has been already fetched by the CPU, and now CPU requested the next instruction 001, uh, and this is also 1 byte. Okay, so this way it is called logical address. Okay, CPU knows the this particular address. The CPU wants to know the instruction that is stored at this particular address. Okay, but this is in relation to the process only. Okay, there is another memory unit called main memory, which is RAM, random access memory. So this particular process is loaded into this main memory, and this main memory, and then the particular instructions are basically stored here on these addresses. These are the addresses, uh, physical addresses. Okay, they are known to your computer. Okay, so whenever the CPU requests an instruction which is stored at 001, okay, your computer do not doesn't know that what is 001. Okay, it knows that there are these addresses. Okay, so the operating system comes in as a middleware and translates this particular instruction, sorry, the address, logical address 001, into a particular address of main memory. Okay, so you can see here, for example, for example, 001 is the logical address. Okay, that is requested by the CPU. And as you can see here, 0, whatever is stored at 001. So as you can see, so whatever is stored at 001, let's say it is stored here. Okay, it is stored here at 111. So now it is the OS responsibility to convert 001 into 1111. Okay, this is your physical address and this is your logical address. Okay, so similarly, so this is your physical address. Okay, these 00001. Okay, so yeah, so these are your physical address. Okay, and similarly they also store 1 bytes of data. Here will also be 1 byte is stored, and so on. As you can see there the address is used by 4 bits. So 2 raised to the power 4, that means there are 16 locations or 16 addresses. Okay, and each address stores 1 byte of data. So 16 addresses will store 16 bytes of data, and that will form your RAM, random access memory size. And similarly, your process size can be calculated. You can see how many locations you have. You have 8 locations. Okay, and each location is of 1 byte. Then that means 8 into 1 byte, it is 8 byte your process size. Okay, it is your process size. So now if you go down, you can see there is a page. So you can see that this is your process, and this process is divided into fixed size of partitions, and this fixed size of partition is called a page. A page has multiple addresses, multiple logical addresses. So you can see here, this is your 000 and 001. These two addresses form one page, and then other two addresses form one page. Okay, this is a fixed size, and as you can see, one page is of two addresses. That means 2 bytes is the page size. 2 bytes is the page size. So okay, so here you can see there is a frame. So main memory is also divided into fixed size of partitions called frames. Okay, so you can say that the page size must be equal to frame size, have to be equal to frame size. Okay, this was done to prevent the fragmentation problem. Okay, in paging. Now there is a page table. So as you can see that your process is divided into multiple pages. Okay, page 1, page 2, page 3, page 4. Now these particular pages are stored in which frames? Okay, as you know that these process instructions are stored in main memory, but since main memory is also divided into frames, so this particular page, as you can see, this particular page gets loaded into main memory, and main memory has a frame. Okay, and as you know that frame size and page size are equal, so a full page will occupy a full frame. Okay, but there is a frame number and there is a page number. So so let us also assign, so there are 4 pages, so then you can do 0001 10 and 11. These are the page numbers that you can assign in binary format. Similarly, you can assign the frame number to the frames in binary format. So here you can see what is page table. Page table is a mapping between page number and frame number. Okay, as in which frame is stored in, sorry, which page is stored in which frame. Okay, so which page is stored in which frame. So here your page number 0001 10 and 11, so they are stored in which frame. So here some bits are used to store frame number. Okay, as you can see, for page number there are 2 bits are used. Similarly, so let me see. Yeah, so you can see there are 1, 2, 3, 4 bits are used to represent a physical address. But from here you can calculate. So let's say if your page size is 2 bytes, and your as you can see, your main memory size is 16 bytes. So 16 divided by 2 is 8 frames. Okay, so you will have 8 frames, and for 8 frames you will have 3 bits. Okay, you can see log base 2 of 8, you will need 3 bits to represent a frame. So here you can see, for frame number you will need 3 bits. Okay, and there are some extra bits that you can see uh, alongside a frame number. So you can see here, if your frame number has X bits and extra information, for example dirty bit or valid bit or some other information is stored, then that will use Y bits. So then your one page table entry will have X plus Y bits. Okay, so so this is your one page table entry. Okay, this particular, this this whole row is of entry of what? Entry of page table, and this entry has a size of X plus Y bits. Okay, where X is your frame number, the bits required for frame number, and Y is for extra information. Okay, and as you can see, your page table has multiple entries. So as you can see, the entries will be equal to number of pages. Okay, so page table entries, so number of page table entries will be equal to number of pages. Okay, so here you can see your page table size will become number of pages into one page table entry size. So in the example, you can see there are 4 pages, and each page table size is X plus sorry, each page table entry size is x plus y bits. So this will become your page table size. Okay. And similarly, you can see number of pages. So your whole process divided by page size will give you the number of pages. So this is your process and this is your page, multiple pages. So if you divide your whole process size by the page size, then you will get these number of pages. And the same concept is applied to number of frames, but here you will use main memory size. Okay, and you will divide by the frame size, and frame size is equal to page size, so you can here use page size as well. Now, how many bits are required for page number to represent page number? This is simple. So total number of pages, log base 2 of total number of pages. So you can see in the above example, how many pages did you have here? So for example, here you had 4 pages. Okay, so you had 4 pages. So you would need log base 2 4 of 2 bits. You would need 2 bits to represent a page. So I did show you somewhere, yeah, here. So you can see your page number is of 2 bits, 0 0 0 1 1 0 and 1 1. There are how many pages? 4 pages. So you had need log base 2 of 4, which is 2. And similarly, how to know how many bits are required for frame number? So that is also simple. You will get the first of all number of frames, which is here 8. Okay, and then log base 2 of 8 becomes 3 bits. So this is your bits required for frame number. Okay, and then there is a last thing called byte offset. So from, as you can see, a logical address. So there is a logical address. Okay, and suppose, so in the example you have logical address of 3 bits. Okay, so from 3 bits you divide into two sections. The prefix is used to represent page number and the suffix is used to represent byte offset. Okay, this is called byte offset. So these two sections are formed from logical address. So as you can see in the example, page number had only 2 bits. Okay, so you can see there are 2 bits to represent page number. Okay, so there will be 1 2. So how many left? 3. Sorry, 1 is left out of 3. So byte offset will become of 1 bit here. So now how to calculate it? Page size. So what was the page size? 2 bytes. Okay, so log base 2 of 2 is 1 bit. Okay, so that means that, and here you can see from this example how many bits we are left for byte offset field. 1 bit only, and from the formula also you got only 1 bit. And to understand the significance of byte offset, let me show you. Yeah, so here you can see this is your page numbers. This is your logical address. Okay, and from logical address, 2 bits, initial 2 bits are used for page number and the last bit is used for byte offset. So you can see this is your one page. Okay, this is your one page, and one page has two addresses. Okay, 000 and 001. Okay, so it had 000 001. Now this two bits have been used to identify page number. Now to get the exact instruction or the exact address, you would need one more bit, and it will be either 0 or 1. Okay, so therefore from the page number you will get a set of addresses. Okay, so whatever, how many addresses you have in your page, you will get all those addresses. So your page number is, let's say, 00. So now using 00 you can get 000 001, these two addresses. But how to get a specific address? For that you would need another bit which we call byte offset. Okay, byte offset. So it is used to specify a particular address called address, and that will form your that will be used by a byte offset. Okay, by appending byte offset to the page number. Okay. Yeah, that's all. we'll be seeing the application of this in next video. Thank you.